Hello.
Hello, Raghavendra.
Sorry, ma'am. I got locked out by mistake.
Yeah, yeah,
Where
yeah.
did I leave off?
Please no, share your slides again.
Yeah. Ma'am, where did I stop? I can continue from where I stopped.
Yeah, you were actually, right.
Right here, right?
Yeah, yeah.
Okay. Okay. Right. Right. So as I was saying, gain imbalance. So these are how the constellations look like when you are talking about how a gain imbalance or DC offset imbalance or quadrature skew looks like. Gain imbalance is that your I and your Q are having different amounts of gain that are involved in it. So you can see that this looks as though someone has pulled it from both sides, from the top and the bottom. DC offset imbalances, you can see that it's not actually, the x-axis is not actually at the center, the constellation is not at the center, whereas the y-axis it seems to be at the center. And quadrature skew is that it looks like someone has pulled it from both the corners. That is, your amount of phase difference between an I and Q is exactly not 90. There is some other number that's present over here. So the thing is, we as users do not have to worry about all of these IQ impairments. NI, or rather ETAS, what ETAS does is that they take care of this inside the FPGA itself. So along with these that like transmit control, packet routing, DUC and BDC, what they do is they have another part called as IQ impairment correction. I'll give you an example. So let's say my mixer is giving I, let's say my mixer is giving an I gain as 1.2 and my Q gain as 1. So what I do is, if I am an I engineer who is tasked with getting rid of these IQ impairments, what will happen is inside the IQ impairments, I firstly receive the I and the Q from my system. Right? These are still in the simple format. They're still in the digital format, so I'll actually be able to do some amount of signal processing on them. So what I do is I divide the I signal by 1.2. Magnitude I divided by 1.2 and the Q I just divided by 1, or rather I don't do anything with it. Now what happens is, since my I is divided by 1.2, by the time it comes to the mixer it will be 1.2 I and 1 into Q. Sorry, not 1.2 I by 1.2 and then Q by 1. Now in the mixer what happens is this 1.2 and the gain, that is the multiplied 1.2, get cancelled, and my output at this point is an analog form of I, analog passband form of I. And over here this is analog passband form of Q. So you see, I've actually gotten rid of the actual impairments in the gain that is there by using the IQ impairment correction part. I've only shown you for gain. They do this for everything. They do this for quadrature skew. They do it for DC offset, for anything that's present. Now, how do they know that it's actually 1.2? What it does is they check all of the IQ impairments. For example, let's say I am supposed to check gain. What they do is they run it across all operating frequencies. I started 70 megahertz. They check what is the amount of gain change up until 6 gigahertz. That is their operating range. So for this entire operating range, they map out what is the change in the gain that the mixer gives, and then accordingly they program their IQ impairments code over here to behave in such a way that everything is nullified. So finally, instead of having a signal that looks like a constellation that looks like or this, or maybe it's not centered properly, it looks like this. All of these issues are taken care of, and when you finally look at a proper constellation, let's say a QPSK constellation, it will look properly like this, where everything, all the symbols are in there, or all this, yeah, all the symbols are in the right positions. So this is again abstracted to the user. I'm just telling you these concepts because they are a part and parcel of what a USRP is, and they are corrected by the NI and TTIS people itself. We don't have to do anything about it. This is again just a vector error that occurs when you ignore these impairments. Right. This portion is actually okay. I'll just give you a very brief of what it asks you. So when you are coding, obviously you will have to, since things are reconfigurable inside USRP, the hardware itself is reconfigurable inside USRP. you will have to tell it a specific couple of things. So the first thing that you will have to tell is the device name. Now, I will actually be theoretically be able to connect as many USRPs as I want to my system. So maybe my system has only one Ethernet RJ45 port, but if I connect my system to a network switch, I'll actually be able to have as many USRPs as possible, as long as they're all in the same network and each of them have their individual IDs. I'll actually be able to connect a lot of USRPs. So if I say I want to write a code and upload a code to the USRP, I'll have to obviously tell the system which USRP I'm supposed to access. So for that purpose, we will have to give the device name as the very first thing. So usually when we go with hardware, I usually say this when I do trainings as well. So when we go with a piece of hardware and we're working with a system and a piece of hardware, usually there is a cable that connects to both of them, some sort of interface. Now, your system, like I said before, has multiple software running on it simultaneously. Now, you can see my tab over here. I'm opening a lot of stuff, and any one of these could be capable of accessing this piece of hardware. In our case, the USRP. So let's say I have two pieces of code with me. One is a CISO code, and the other is an OFDM code. Now, obviously, each of these does different things, or it can actually be two separate CISO codes also. It doesn't matter. Now, when you want to access a USRP, which is a piece of hardware from a system using a particular software, the process goes like this. The very first thing is you first name, each of these will have its own separate name. The name could be anything like NI USRP. Usually for a system that has a USB connection, it is something like this, similar to this, not exactly. For an Ethernet-based system, you have your default IP address, which is 192.168.1 dot, sorry, 1.10. This is the default address that's it. 1.10, correct. And then you have, sorry, 1.2, not 2. And then if it is a Rio that is connected using a PCI connectivity, it is usually Rio 0, Rio 1, so on and so forth. So first you'll have to mention which is the USRP name that you have over here. Hello, am I audible now? Hello.
Yes, yes, you are audible.
Okay. Yeah. So firstly, you will have to give the name to specify which hardware. Now after that, what happens is the software opens something called as a session with the hardware. A session in simple terms means that this piece of software, so let's say I'm using OneNote for, and for somehow I'm accessing the USRP with the OneNote. Now, since OneNote is accessing USRP, no other application is supposed to disturb it. So what I do is I do something called as open a session with this particular piece of hardware, which basically tells any other software piece on my system that this hardware is being used right now. So if I have another application, so let's say I have this particular USRP with me, I am using a particular LabVIEW code to run some code on this. If a second application tries to access this, the session will not be given to that application because something is already running this. So that is how we manage a hardware on a software. We open something called as a session, and at the end, we always close the session so that any other software that is trying to access this at a later point can do so. So opening and session or closing a session is actually an important concept. That is how we work with not just NI-USRPs. This is actually with anywhere. If you see an error called as session error, that means one of two things: either something else is accessing the hardware right now, or something else accessed the hardware before but didn't close the session properly. So that is how we interface a GPOS or a general purpose system with any particular hardware that is capable of communicating with it. Now, that is why we give a device name. Post that, you have IQ rate, which is nothing but your symbol rate. We call it IQ rate because we split it into I and Q components. This is nothing but the symbol or the sample rate. Sample rate is actually a better term in this case. After that, we obviously have to set the carrier frequency. You can set anything in the range of what the USRP is capable of. Suppose, let's say my USRP is capable of 70 megahertz to 6 gigahertz, and by mistake you set it to 7 gigahertz. The driver will automatically coerce or force the value to go to the nearest possible value. So if I set it as 7 gigahertz, the nearest possible value is 6. So it will coerce or force it to come to 6. After that, of course, I have to mention which antenna. So I told you, right? You can set RX to either here or here. So you will have to mention which antenna you are using. And of course, you will have to mention what is the gain of the transmit amplifier. Number of samples per buffer. Keep this in mind for now. Ajay will be telling you exactly how this works. He'll be taking the receiver portion of the CISO transmitter. When he comes to that point, he will tell you exactly how and why this is needed. And this is basically how it looks on your LabVIEW platform. This is how you'll be putting it. It's actually pretty simple. You only have to define these six things for your signal and then just give your signal. It will transmit and receive it. Okay, so any doubts up until this point? I'll stop with the USRP part of things here, and then I'll go ahead to how we built the CISO transmitter. Any doubts up until this point? Okay, then I shall continue with the yeah. Yeah, right. So this is a concept that you will understand better when you're looking at the CISO receiver. So I'll ask Ajay to explain what this is to you. So I want to concentrate on transmitter for now, but don't worry. Ajay will explain to you what exactly number of samples is and why we need it. Apart from that, do you have any other doubt? Okay, cool then. I will proceed to the CISO. Okay, right. So again, I'm sorry, this might be a lot of theory for you, but it is actually important to understand certain concepts of this theory before I actually show you the practical implementation of this. So CISO, as you can see, is single input, single output. It is the simplest wireless thing that you can have. You have one antenna that transmits and one antenna that receives. You may think as to why are we doing a CISO when it's the most simplest thing. When you are doing with when you're coding with MATLAB, let's say you're actually doing just a normal CISO thing, this wouldn't take a lot of time to do. Even if you don't have a lot of experience with RF and digital signal processing, this actually wouldn't take a lot of time for you to do because there are not a lot of synchronization processes that you'll have to use over there. Since you have a singular code over there and everything goes in the form of variables, you don't have to worry about code being synchronized or the code basically knows exactly what's being transmitted and there is no delay as such that is involved in a MATLAB code. But that is not the case when you come to a practical scenario where you use an SDR. In fact, you might have heard this where they say that a paper has more value if you have actually put some results with respect to a hardware, simply because a hardware involves a lot of practical issues. And if you write a paper that solves all those practical issues along with the core concept that you have, it has a lot more value because you're solving a lot more problems than a paper that just has a MATLAB code in it. Of course, even that is valuable because you're introducing a new concept, but this you are solving more problems along the way. So it has more value in that sense. So again, usually CISO packet transceiver, we are done it as a packet transceiver. It's not just a CISO link. It is a packet transceiver based system where we split data into packets and then send them. The why and the how I'll be coming to in the coming slides. Also here I'll be switching a lot to one note because there are a lot of concepts that I'll have to explain. So please bear with me on that. Right. So we usually transmit digital signals because they are better equipped to deal with noise and channel effects. Or to put it in a better way, we are able to deal better with noise and channel effects when we are sending digital signals. Like I said, source coding is the very first thing that we do. Essentially, it is compression. You try to reduce the amount of transmit data simply because one, transmit lesser data implies lesser time required to transmit, and two, lesser data implies lesser amount of lesser amount of effort you will have to put into correcting the transmitted data. So received data will obviously have impairments, and if you have lesser transmit data, you can receive it faster, and the amount of corrections that you have to apply is also less. Source coding techniques are some of them you might see over here. These are academically, a lot of you might have seen the Shannon, Fanon, Huffman, and in fact even Lampel did. But actually, these are all lossless types. And you have also the lossy ones like JPEG that you have for your images, MP3 that you have for your images, etc. Usually we use JPEG, MP3, and all of that simply because a little bit of noise in your audio and your image doesn't really affect the quality a lot. But when you're talking about things like text, even a small amount of noise will actually tell you that there is some impairment in the signal. I'll tell you why. So let's say I have a text. I am sending sorry, A, B, C is what I'm sending. So how we send the data is we first convert these into their respective ASCII characters. So it is 96, 97, and 98 are the ASCII numbers for these three characters. And then we convert them into their respective Boolean values. So 8-bit Boolean value is assigned for each and every character. So let's say this is 1, 1. I'm just giving you an example, 1, 1, 1, 1, 1, 1. Now, if there is even a single bit flip over here, so let's say this is for B, so let's say 1110 is for A, 1111 is for B. Now by mistake, let's say if I want to send B from transmitter to receiver, but then this bit flips in the middle, it becomes instead of zero, instead of one, it becomes zero. Then I actually receive an A over here, which is not correct. Which is why when we try to send text data, especially, we always try to ensure that it is a lossless compression. If you're using any compression techniques, we usually ensure that they are lossless. That's the difference between losses and losses. But whereas for an image, you might not keep looking at maybe one pixel is off, but the rest are fine. You wouldn't really mind that. Even in a video, even if just one pixel somewhere in the corner is a little off than what it's supposed to be, you usually don't mind that a lot. Same goes for an audio. Right. Now, coming to channel coding. Now, again, as you might know, channel coding is something that we do. We add redundant bits to our signal simply because we are sending all of this. In fact, even a wired channel will have some amount of AWGN noise, some amount of electromagnetic interference involved in it. And sometimes channel coding is required for those as well if you're sending it for long distances. And if you're talking about wireless channels, though, it obviously will have to require because the number of obstacles and the number of places that the signal goes to is just much larger. So obviously, we'll have some amount of distortion, not just in amplitude but also in phase. Now, your inherent channel distortion along with AWGN causes bit error rate along with intersimple interference. Intersimple interference I will address in a while. So for now, BER, bit error rate is as in you'll actually get a lot of bits that are flipped. Instead of zeros, you have ones over here. So you will have to have some sort of method to correct for them. What we do is we try to identify these bit errors and then reverse them by doing something called as channel coding. Now, there are actually two things that you can do in channel coding. Some of them are called error detection systems and some are error correction systems. Now, in error detecting systems, we just see if there is an error or not. Some of the simpler ones are simple parity check, where you just check the total number of whether the total number of ones are odd or odd or even, and then you check the same at your receiver send as well. You add this parity value to the end of your packet, and then you send it to the receiver. The receiver checks this. If the parity value seems to be off, then the receiver realizes that there is some error in the signal. Similarly, checksum will allow you to see if all of your data has actually been received in the correct format. Same goes for CRC, cyclic redundancy check. Now, you also have error correcting systems like Hamming and convolutional. Now, you might come up with a question saying, if I already have an error correcting system, why do I have to go with an error detection system? There is a reason. Now, error correction systems, Hamming, you might have seen this or you might have read it somewhere that Hamming is only capable of detecting up to 2 bits error and correcting 1 bit error. Convolutional coding is not the same. It will actually be able to correct most errors that are there in your signal or your bit stream that's there. But the problem is convolutional encoding multiplies your data volume a lot. So if I say the convolutional coder's rate is 1 by 2, that means that I have X amount of data bits that I want to send out, but because of convolutional coding, I'm actually sending out Y amount of data signals. There might be shorter packets or scenarios where your wireless data is not always completely corrupted. There is only a chance, maybe a 1 in 10 chance where your data might be corrected. In those cases, what we do is we do something called as a retransmission architecture, where we send from the transmitter, we do an error detection. By the way, error detection does not require a lot of redundant bits to be added. the number of redundant bits that are added is actually less compared to error correcting. So we add a small number of bits and then send it. If there is an error, this receiver system simply asks the transmitter system to send the data back. If the amount of data that is being transmitted between transmitter and receiver is small, error detecting system actually makes sense because the volume of data due to error detecting being applied is actually very less. Whereas error correction, the volume increases by a lot actually. If you want me to give you examples of what this exactly is, just a second pointer. So if you want me to give examples of what error detection systems or where they can be used, they can be used in sensor-based IoT systems. Yeah, I've actually used error detection. I've used CRC in error detection systems for an IoT-based sensor system, which allows to send meter data from one place to the other. So that particular system that I used was called as LoRaWAN. It stands for Long Range Wide Area Network, and it can only send 51 bits at a time. Sorry, 51 bytes at a time. So that's not really a large data volume, and the amount of the probability that there will be erroneous bits are pretty less in that, which is why we go for error detection systems. Any doubts? Anybody? Okay. Again, these are just examples that I have put in over here of to what a checksum and a symbol parity check looks like. You see parity checks, I only have to add one parity there. Checksum, have to split it into blocks and then add the number of total size of the checksum won't be all that large. Right. Now coming to the aspect. Also, whatever I'm doing over here is all based on the transmitter. Whatever concepts I'm saying is transmitter concepts. And I'm doing it in the order that we've actually implemented in the CISO packet transceiver code. So first we do a source coding, channel coding, followed by modulation and decodation. Now, although the data itself is digital, whatever is transmitted has to be analog. So modulation, you would find this probably in most textbooks, is essentially converting information in a manner suitable for transmission. Analog modulation, you usually would have been used to the concept where you send a signal like this. Modulation, you would say, is changing the characteristic of a carrier signal, which looks something like this, using a message signal to ensure that it is transmittable over a wireless scenario. Reasons you would know: antenna length, distance of transmission, whatnot, interference. So the convention, this is what most textbooks say, and it is correct. Even for digital, like if I talk to you about BPSK, and if I say these are my bits, what you will imagine when I say BPSK modulation is this. You have this over here, and then you have a phase change over here. Again, you have a phase change over here. Again, you have a phase change over here, so on and so forth. This is technically not what we do over here, although the definition itself is correct and that's how it's supposed to be used. This is not technically what we do over here, simply because all of this is being taken place inside your general purpose operating system, inside your PC. So what we mean when we say modulation or demodulation is, so let's say I am doing a QPSK modulation, where if I draw my constellation diagram, it will be these 4 points. Where, of course, all of these have to be gray coded. In a QPSK, we know that each symbol is mapped to 2 bits. So this will be 0, 0, this will be 0, 1, this will be 1, 0, and this will be 1, 1. Oh, sorry, this will be 1, 1, and this will be 1, 0. We are gray coding it. So it has to be like this. What happens is, if I say receive a stream of 1, 0, 0, 0, and then 1, 1, I'm actually supposed to convert it to these QPSK symbols, and the actual value, the I and the Q value of this would be 0.707 plus J 0.707, and then for this it will be minus plus, for this it will be minus minus, and for this it will be plus plus. When I say modulation, I am simply converting these bits into these symbol values. So if I say 0, 1, I'm actually converting, when I say modulation in terms of what I'm talking about in an SDR, I am simply converting it from 0, 1 to minus 0.707 plus J 0.707. 707. When I say 00, I am converting it to plus 0.707 plus j 0.707. 1 is minus minus. That is all I'm doing. I am not involving any carrier frequency at this point of time. Carrier frequency involvement will happen inside the USRP when we are doing an up conversion process. We will make sure that our symbol is, or our signal is coded in such a way that our final result will look like this. But at the moment, we are just converting it from bits to symbol. This is called as a bit to symbol conversion. Anybody has any doubts up until this point?
Hello, Raghavendra. You have a question in the chat box.
Chat box. Okay, I just
This is from Shailesh. I'll just
okay.
read the question for you.
Sure.
Yeah. The question says, what about the codes like turbo codes and the LDPC codes, which